Let's work on some curve fitting. We're going to use finite differences to determine the degree of a polynomial that will fit a given set of data. We're also going to use technology to find polynomial models for a given set of data. Finite differences, those are the first differences, the second differences. If you remember when we tried to decide whether data gave us a quadratic model, we did a lot of second differences, because if our second differences were constant, then it was a quadratic model. So now we're going to try to figure out if it's linear, quadratic, cubic, etc. So finite differences can be used to identify the degree of any polynomial data. Finite differences, that means we're going to take the y values and find the difference. And remember, we just have to go in the same order. It doesn't matter what order we use, it just has to be the same. So if I'm going to move from left to right, -2 minus 4.3. That gives me -6.3. 4.3 minus 8.3. -4. 8.3 minus 10.5. -2.2. 10.5 minus 11.4. -0.9. Again, we're just going to keep on going. I did not need a calculator for that one. Actually, I didn't need a calculator for any of them. But we have our first differences. Okay, I'm going to push pause and go ahead and do my second differences and my third differences and see which one gives me a constant, or which one closely is pretty close to giving me a constant. So you see, when I did my third differences, I got -0.5. If you go down to the chart in the previous slide, that means our data is cubic. That's all we're looking for with that one. Okay, you try this one, use finite differences to determine the degree of the data. You're just going to take each number and subtract it from the number next to it, and you just have to go in the same order. I'm going to move left from right again, so my first one will be -9 minus 16, which will be -25. 16 minus 26, -10. 26 minus 41. 41 minus 78. 78 minus 151. Okay, our first differences do not work, so go ahead and figure out what the degree is by doing the second differences, third differences, until you get a constant. I'm going to push pause. So if you see here, my fourth differences are constant. So I have a quartic polynomial. I apologize, this is you try. I'm not going to do anything here. You guys work it out on your own. Push pause. So that would be a cubic polynomial. Alright, next example. Once you've figured out the degree of the polynomial that best describes the data, you can use your calculator to create the function. So here, the table below shows the population of a city from 1960 to 2000. We're going to write a polynomial function for the data. The first thing we need to do is find the finite differences of the y values. We need to see what degree it is. So I'm going to go ahead and push pause and do a lot of subtraction, and I'll push play in a second. So what you see here, the differences, the first differences, the second differences, and the third differences. And here with the third differences, we are going to say this is close enough. And take this as a cubic polynomial. The next thing we're going to do is put this into our calculator. Okay, we're going to do our stat edits, and this is going to be list 1, and this is going to be list 2. Now, the crazy thing about list 1, if you try to remember some examples we did back in quadratic regressions, years we cannot plug into our list as years. The calculator thinks that first year is 1960, and it's not. It's 1960. So what we need to do is plug that in as a 0. 10, 20, 30, and 40. So list 1 cannot be the years. It has to be 10, 20, 30, and 40. And let's continue the problem. Now, what you see here, we just did the stat edit, list 1 and list 2. And then we go back and do stat calc. We said it was cubic because the third differences were close. So cubic regression, which you see right here. So if you push enter, possibly a few times depending on your calculator, this is what you will get. And you need to go ahead and write your equation. What I want to point out right here is the r squared value. And if you remember, the r squared value, the closer that value is to 1, the better your data is. So our function is actually f of x equals a plus b plus c got a little long plus d. If you see, I'm just keeping the same amount of places past the decimal place as everything else, which actually this one, this a, should be, I don't know if I'll be able to squeeze it in now. Okay, 2 places past the decimal place. So that is our cubic regression for that set of data. Okay, let me look real quick at something. Yep, we're good. Okay, the next one's, so go ahead and find the finite differences. Okay, figure out if it's linear, quadratic, cubic, quartic, or quintic, and use list 1 and list 2 and do some linear regression. I'm going to push pause. You go ahead and go to work. So there we go again. Our third differences are pretty close. All of those numbers would round to 1, so we'll say that they are pretty constant. So we'll go ahead and do list 1 and list 2, stat, edit, etc. We'll do a stat, edit, list 1 and list 2. That looks awful. Erase. List 1 and list 2. Once we get that data in there, you go back and do a stat, calc, cubic regression. And then you'll hit erase, enter as many times as you need to, depending on your calculator. And that is what you'll get. Okay, our r squared value is very close to 1, so our function looks like this. 0.0010 x squared, nope, x cubed, it's cubic, minus 0.11 x squared, plus 4.13x minus 24.87. Okay, written crazy, but that is our function. That's all we have for today.